Alright guys, so let's start with lab session number 5 for this deep learning course. So welcome all, first of all. Sir is actually not present today, so that's okay. I'm actually recording this lab session on my own laptop, so this will be recorded. So let's get started. Can you all see my screen and hear me?
Yeah.
Yes.
Alright, wait now. Alright, so in today's lab session, we're actually going to continue our discussion on computer vision. And last time we actually looked at like the basic application of computer vision, which is how to implement like basic convolutional neural networks. This lab session, we're actually going to look at more advanced convolutional neural networks. And we're going to pick up specific problems that have been solved using, modifications to the existing architectures that we've seen. And so in today's lab session, we're going to look at like one of the most important applications, which is known as image segmentation. So let's actually take a look at what image segmentation actually is. Now, image segmentation looks something like this. Oops. And I would give my model an image and I would expect my model to tell me which pixel belongs to which category. So it would rather tell me that this pixel belongs to the category car, or this pixel belongs to a road, and then this pixel belongs to a building, and then this pixel belongs to a tree. And I would expect it to sort of give it a color code or sort of a code to each one of those. And that is what will and so for this is actually not such a trivial problem, because I'm expecting my neural network model to understand the semantics of the problem itself. So it's not just um, a cat versus dog, but now is to understand like sort of the structure of various things, like and so a cat or a dog, like there may be a cat in the middle of the image, and the model somehow yes, Akshat, the recording has been started. Not on this lab session, but I'm recording it on my own computer. First thing first, let me actually share this the link to this notebook. And I'll request you guys to sort of answer to anyone in the chat if someone asks if the recording has been started of the notebook, or if they ask for the notebook. So please give that to them. Give me a second. Right. Right. And so, let me. Yep. And so, when last time when I gave it images of cats and dogs, I expected my neural network model to sort of understand not only, so even if there were like trees and everything in the background, neural network didn't have to care about that all stuff. But now it has to go inside the inside the image and sort of like analyze the structure of what a road looks like, or what a car looks like, or what a wall looks like, a tree looks like, a building looks like, so on and so forth. And look at this, even the street lamps have been given a certain code over here. And so it starts to become more and more complex. And so we'll solve that kind of problem this lab session. um, First thing first, so let's before we actually get into sort of the problem itself, like solving the problem, let's actually do some basic setup. So for that, first of all, I hope you guys have opened a Google Colab notebook and you're ready with me. First thing first, I'm gonna actually convert. So this time we're actually gonna use a GPU. So what I'm gonna do is I'm gonna go to change run type. Okay, fine. I'm gonna go to runtime, change run type, and in the hardware accelerator thing, I'm gonna go to GPU and save. All right. And so now, what what I'm gonna do is I'm gonna do some basic importing. So import torch, so PyTorch. We always import the neural network library, so torch import nn, because otherwise you'll have to write torch.nn and stuff like that. Computer vision problems, a lot of important stuff is given in the torch vision library, so torch vision. And we're going to be dealing with images, so we need something to deal with images, so import image. All right. And so, and I'm actually going to be downloading some data sets, so I'm going to need to navigate within the system itself. So for that, I can do that using two ways. One is I can do direct Linux sort of commands, or I can use modules that have been designed for Python that do the same exact job. So there's OS, and there's from pathlib import path. All right, let me execute this. All right, so done with that. And so now let's actually download a data set. So for this data set, I'm actually not going to download anything from Kaggle or something like that. I actually, because this sort of data set was actually very fragmented, so I've taken the liberty to sort of save it in a Google Drive. So I'm going to ask you to copy this drive link folder. Don't open it. And so just paste it over here and say file is equal to open double quotes and paste it over here. All right, so that's all the basic setup that you guys need to do from your end. So this is actually sort of a drive link, drive.mount/content/drive. All right, and so once you do that, I'm gonna do that again. Once you press enter that, you're gonna get a notification that asks you to connect to Google Drive. You press yes. You press whatever account you're going to use. Most likely it will be the Google Drive in which you've stored this. If it's a BITS account, then you choose your BITS account. If not, you're going to choose the other account. X allow. So each time you're going to need to do this once. That's why I don't like all this mounting stuff, because it's not everything. I mean, because now you have to manually intervene to run a notebook, and for someone, if you're going to share this notebook to someone, he's going to have to download the notebook again. And so what I usually like is to sort of directly download it on the run. That's usually much better and a much faster way to do that. But I'm going to go %cd. So % is magic inline, which means that when you do an exclamation mark, it's a very temporary thing. So because now you actually want to change directories permanently, so you want to do % rather than exclamation mark. All right, and so you're gonna go cd/content/drive. It's okay to put it in quotes as well, and navigate to the folder in which you've put your folder. So for that, you're gonna go drive/my drive. All right, and so my drive is the place where you're gonna have like sort of all your what do you call folders and stuff like that and whatnot. And so I have a lot of stuff over here, but where is it? Portrait.zip over here. All right. And so what I'm gonna do is I'm gonna do unzip portrait.zip. Let's go to the unzip Linux sort of. I want to actually save it by the name of a particular file, and so I believe it's -f something, but let's see. Oh, there's D. All right, and I'm gonna name it portraits. All right, and I'm gonna go. All right. And so it's gonna unzip it into that folder. And we're gonna take a look at the structure of the files as well. So that's totally fine. All right. And now what I'm going to do is I'm going to go back into this portraits folder permanently. And let's actually do a sort of an ls to see what exactly data is it that we have over here. So you will see that there are folders, that is GTPNG, images, data crop, train.txt, validation.txt, and some other folders, e.g. 1800 and whatever. So we don't actually need this, we're actually concerned with just these four over here. All right. And so let's actually talk about like what exactly these is it that they contain. So if you wanna, all right, so let's actually, so what is it that this data set contains? So this image data crop contains images of people. So the data set that we're actually dealing with is called portraits, and it contains portraits of humans. And so our deal is to sort of do a bind, so sort of to create do a segmentation as to say which pixel belongs to the person's face and which pixel belongs to uh, uh, which pixel belongs to the background of the person. So that's the kind of classification that we want to do over here. All right. And so let's talk about like how exactly is it that we actually do this segmentation. So what actually, how do you think that this model does sort of this color coding over here? The way that model actually color codes different sort of pixels is sort of it creates something known as masks. And masks are nothing but like sort of images of the same dimensions as your input image, except that each pixel is given a certain number. And so the numbering goes from 0 to n, in which n there are n plus 1 classes. Let's say for example, so for example, 0th class would correspond to a road, and 1 would correspond to, let's say, a car, and 2 would correspond to um, a person, 3 would correspond to an electricity pole or stuff like that. And sort of the ground truth PNG is basically, I mean the ground truth would basically be an image of the same size, except each pixel is now numbered either 0, 1, 2, rather than the input image would be something like an RGB image of 3 channels having 0 to 255 values. Ground truth would be a single channel, it contains 0 to n values. So that's it. So that's about that. And so I would sort of let's actually go to images data crop and ls to let's see what exactly images that we are dealing with over here. And so there are JPEG images over here. All right, let's try to open one image. Let's say for example this. So I think it's image.open. All right, so you go sort of image.open sorry, what is it, what is the folder's name? Images data crop slash this. Let's see. And so you see that these are the kind of input images that we have over here. Let's actually also go to ground GTPNG, which contains the output labels for these, which are not like now dogs or cats or single labels as such, but they are images themselves. And so we go to GTPNG. And you contain stuff like that. All right. So now if this was 00507, I would assume that this would be something like sorry, I would go image star open. This would be GT PNG, and this would be PNG, and this would be mask over here. I would assume so. Just a guess. And yes. So look at this image over here, and look at this image over here. So this is actually, and so this is actually nothing but a sort of a sort of a map which contains zeros for let's say the background and one for the person's pixels. And so we're sort of doing a binary classification for each pixel which either be categorized as sort of a background pixel or a pixel belonging to a particular person. Now, all right, so that's about that. So we need to
I
extract.
have a question.
Sure.
How do you make this data set?
So there are tools for that. Uh, there are so okay. So for that, I'll actually refer you to a few papers as to the segmentation images and how to do that. I don't actually know the names of the tools, but let's actually search for that. Image segmentation. Image segmentation dataset tools. So I see a few website over here. Polygon annotation tool, introducing image segmentation at label box, and there must be other software as well, and that's exactly how this is done.
So it's mainly manual work only. You have to select the region.
Well, I mean, technically it has to be manual, all right, but people actually do use when you go into research, you'll probably see that what they do is that they use previous model to get sort of a rough outline, and then they do manual work to sort of correct the edge cases, edge pixels.
Hmm.
So that's about that. I mean, so you can actually reduce this entire manual pixeling into, you can sort of reduce it by 99% as such. That's about that.
Hmm.
That's all. But
Okay.
yes, manual. All data sets are manual as such at some point. You can make it easier, but there has to be manual intervention because you're talking about ground truths, and so ground truths is basically something that is set by human standards. To be fair, I've actually seen people use sort of generated data as the ground truth labels as well. So that's a very recent thing. But again, that comes from a sort of a human bias, and human intervention plays a role at least some fundamental level. All right. I'm going to be extracting all these images and putting them into sort of what do you call classes and sort of files, relevant files. And so for that, you would sort of see that there's a sort of discrepancy. So um, these are JPEG images, the ground truth images, and the remaining are PNG images. So I need to sort of incorporate that as well. So let's just actually start writing. So I'm gonna write. There are image extensions, and so the allowed extensions would be JPEG and PNG as well. So now I would go def get images, which is sort of a way to get uh, mm, sort of extract all images together and put them into one particular place. So extensions is equal to image extensions, and so I'm sort of giving a flexibility like whoever wants to change these extensions can actually also change it whenever they want to. So path is equal to, I'm going to change it to a Python object, which is going to be path, and I'm going to go def ends with file extensions list, which is also going to be a list. And so I'm going to go and I'm creating a sort of a doc string over here. So this return doc string is basically like, do you guys remember that whenever we want to check the definition of a function, we used to do question mark followed by something? So by default, it actually, for functions, for classes, the question mark returns the repr. All right, done the repr. And for functions, it returns a doc string if possible, which is basically the very first sentence string, which is actually put just below the def part of it. So returns true if file ends with either of the extensions in the given list. And so this would be so initially I would do res is equal to true, and for O in extension, res is equal to res or file dot ends with O, right? And I'm gonna return res. And so if it ends with either of the extensions, it's gonna return true. All right, so that's that. X is equal to so I'm gonna initiate my x's as a sort of images as such, sort of a list. And so I'm gonna say I'm gonna iterate through the entire sort of directory iteratively in os.walk path. If ends with file extensions, I'm gonna do x dot append path p slash file. Oh no, so f is gonna be a list of files. So for file in f, I'm gonna do if ends with this. All right, that's that. And finally, I'm just gonna do a return x. All right, so path is gonna be current path, which is where am I? So path, I'm currently in whatever path I am, and so I would sort of do path this, and I would say f names, which is the names of the files, is equal to get images, right? That's the name of path slash images data crop. All right, and let's sort of see if this works. There's an error, path is not defined. Oh, sorry, shit. Okay, I'm gonna have to import the path lib again because I've just redefined path, which is not acceptable. All right. So let's actually look at f names 0, and so that will actually be, what is f names? F names is an empty list. If ends with file extensions. All right. So let's actually see what's going on over here. Printf. (2003) So I'm just trying to debug this over here. Google Colab is sort of, so what exactly is the problem over here? So for file in F, printf, oh, print file. For O in ext, res is equal to res, or file dot ends with, oh, this should ideally work. Oh, I didn't return anything. Yep, it works now. Alright, so I'm gonna remove these prints over here for now, and let's actually see f names 0. And so I would get sort of the path of the images themselves, so that would be the file names, and so these are my x's. Alright, so now I need to check for my labels as well, so I'm gonna create a name of labels as well, so I'm gonna name them as label names is equal to get images path slash gt png, right? And so f names and yeah, so now I'm gonna have that and that.
Could you explain the get images function once?
It's nothing, it's just a function. So let me just write it here. It's a function that returns a list of all files with the given extensions in the given path. So when I would pass it this gtpng, it would iterate through each file in gtpng, and whichever file is an image, it's gonna return that to me in form of a list. And the reason I'm doing this because this usually contains it may contain, and I'm sort of giving you flexibility. Many a times your dataset directories also contains other files like text files or sort of configuration files and stuff like that. And so if you're gonna pass that, if you're gonna assume that that is also part of the dataset, somewhere down the line it's gonna give you an error because your model is gonna be expecting images. And so that's about that. So I'm sort of writing a path. I'm sort of going through all the path, and I'm checking that does this file end with the given, with any of the extensions given in this list, which is in this case JPEG or PNG, right? And if it does,
And ends with checks if it's ending with
yeah,
JPEG.
it's a string operation. So string
Okay.
dot ends with sort of so this is so
Understood.
yeah, right. So what I'm gonna do is that assert I'm gonna check if these two have the same lengths. LBL names is equal to len. Now it may or may not be true, but so I want to show you something. Assertion error. Alright. So len f names, len label names. Alright. So now here's a sort of a mismatch over here, and so now you see that there are actually a few missing files over here. So I don't know. Let's try to look for some. 237, 238, 239, 240, 51, 52, 53. This ends with 2632, and this sort of ends with 2362 as well. But anyways, it so happens that label names contains more number of JPEG/PNG files than does F names, and so there's a sort of mismatch between the two, right? And so as part of pre-processing, or as part of data cleaning and data setup, what you need to do is you need to sort of set up a sort of mapping function which says that for any name in F names, what's the corresponding label name? And it's very simple. Like, I can do it visually. It's as simple as, like, there is 00496.jpg that would be converted to 00496 00496 mask.png. All right, so I need to sort of write that mapping function as such. We'll do that, and let's actually take a look at that. So let me take a random image. Let's say function is equal to, what was the image that I was actually talking about? 00485, let's say. All right, and so that would be 0045 dot 00485, right? So that would be ID. So ID. All right, and so what I'm going to do, image is going to be image dot open f images data crop slash ID, right, dot JPEG, and so the corresponding mask would be image dot open f GTPNG slash ID mask.png, right? And so let's look at I am right now and mask right now, right? So you see that there is a few errors over here, and that probably means that there is an error in the data set itself. All right, but overall these two definitely do correspond to the same images as such. And so let's actually look at, like, what exactly do these look like. So I'm gonna name this def to tensor, and I'm gonna name it image, and so I'm gonna do return torch vision dot transforms dot to tensor. I need to initialize this first, and then I need to pass in the that itself, the image itself. And so now what I can do is that I am tensor is equal to tensor image, and so we're gonna, and mask tensor is equal to tensor mask, right? And now I'm gonna do imtsr.shape mask tsr.shape. So look at that the input image is actually 3 channels, 800 by 600 width, all right, which is this image over here. Right, but this is only one channel, 800 by 600. That's that. All right, that's that. All right, so let's actually now so now we need to actually build a data set. Now we built our data sets before, and to do that we actually sort of package our x's and y's together, but instead of now y being a sort of a label, it's an image itself, so we need to take care of that. So I'm going to be building my data set now. Text building my data set. All right. And so for that, I'm going to do, I need to import some basic libraries. So from torch.utils.data import dataset, which is basically the equivalent of nn.module for architectures. For datasets, I need to have some basic functionality which I don't want to write from scratch. So for that, I'm going to be importing dataset. All right. Random split, because I actually also have to split it in an training and validation data set, and data loaders, of course, which we're going to use it to package all our data into batches and sort of feed it into the GPU and stuff. OS is already imported, images already do that. So okay, anyways, so class segmentation data set, and it's going to be a child of the data set class. Def init, right, self x path y. So I'm gonna pass it the path of the x itself. All right. And I'm gonna pass it, instead of passing the path to the y, I'm gonna pass a sort of a function. All right. Which sort of maps a file from the x part to the y path itself. All right. And what I'm gonna do after that is so for that I'm actually gonna have x and the corresponding y's in that particular order. All right. So that's gonna be yfn. So by default it's gonna be none. All right. And of course, look, by default I'm not gonna save the images themselves, because images are of very large sizes. So rather that what I'm gonna do is that I'm gonna only store the path of the file, and I'm gonna sort of apply a transform that converts images to sort of file parts to images, and then images to tensors on the fly. And to do that, I'm gonna be defining transforms. By default, they're also gonna be none, and optionally you can also do transforms on your y, because now your y transforms are also sort of images themselves, and so they also can have images on them. That's about that. All right, that's that. So I'm gonna do self.transforms is equal to let's say it's gonna be transforms, but let's say if transforms is none, so I would rather have I would rather like to return only what do you call the image itself, so the file itself, without doing sort of any sort of operation on them. And so it's sort of an identity transformation, like it does nothing at all. So that's basically this function over here. It's a lambda function. If not transforms, right, else transforms, right. And sort of self.y transforms is also going to be sort of similar, right? So it's going to be lambda x if not y transforms, else transforms, right? Self.x fnames is going to be simply get images. And I've taken the path of the x path, the path which I've given over here, and self.y fnames is going to basically be this function yfn applied to each image over there, each image in self.xname. So yfn I for I in self.xfname. So is that clear? Right. So that's basically, I've now self.x and self.y, except these are not images, these are paths of files, and we're going to transform them into images on the fly. Means whenever you want to access something, we're gonna apply the transform. So now you see that I would sort of have to modify my self.getItem, dunder item, which is basically responsible for retrieving sort of any sort of data. So next is any data set also contains dunder len, all right, self. So I'm going to just do return len self.xfnames, all right. And now the most important point is how do you retrieve any data. So for that I'm going to do get item and self dot index right over here. And so now what I need to do is I need to sort of apply transforms. So I need to return image and the corresponding y also. So that is also an image and they're going to be a tuple. So I'm going to do self dot. Let me actually write a function that applies all the transforms. So apply tfms self x tfm list. Alright, so and what this basically does is that for tfm in tfm list x is equal to tfmx. That's all. So it applies a transform in that particular order, and I'm simply going to be returning x over here. And self dot apply tfms. What does it take? X is self dot x f names I, right? And self dot transforms. I need to also apply and the same thing again for my y's as well. Sorry about that. So self dot y f names I, and I need to and self dot y f names if at all there are any. All right, and so that is about that. Let's see if this works. Invalid syntax. Oh, I didn't put an equal to sign. Right. So let's actually now build a data set. So it's going to be segmentation data set, and its initialization I'm going to put in x path is equal to what? Images. Should I? Yep. So I've ensured that it gets converted to the path object, so I can just directly pass in the string over here. So that's going to be images data crop. Alright, are you guys following me? If you guys are falling behind, feel free to like refer to this notebook and jump where I'm doing, because this is really important stuff and really important concepts. So YFN is basically a function that maps a file from X f names, which is the file names from the images data group directory, and sort of gives the corresponding y name. So now look at how I'm creating this function. So it takes an input, which is basically the file name of the image over here. So that's going to be something like this, like sort of images data crop /0001 /.jpg. I need to return the corresponding png file from the other directory, and so that's going to be simply, I'm going to be returning path gt png slash wait, and slash f x.stem, which is basically every file name contains of two parts. There is the stem and the suffix. So 0001 is called the stem, and dot jpeg, so jpeg is called the suffix. So I'm extracting the 0001 part. All right, then there's mask, right, and then there's png. All right, there's that. All right, so now even though my y directory contained more number of files, that's okay, because I'm only going to be extracting y for those files which exist in the x path, right? And so I've sort of solved that issue as well. And so transforms are basically going to be the transform that you're going to apply on your x's. So first of all, it's going to be and it's going to be a list of transforms separate, and each transform is basically a function that you apply on whatever input you give. So initially you have a file path, so you need to do image.open, so it sort of opens it. All right, next you pass in you sort of convert it to RGB, because I'm not exactly sure if what exactly is the format. It can be of anything. Image.open basically has many formats, and I'm not exactly sure what it is. So just to be sure, I'm going to put it in RGBs for consistency purposes. All right. And so lambda img dot convert RGB. All right, and basically this is nothing but til image dot convert. So returns a converted copy of this image. For the p mode, method translates pixels through images. Anyways, blah blah blah. So you can sort of convert any images to black and white or grayscale or HSV format, or to sort of grayscale formats or RGB formats or BGR formats or whatever you want to do. That's that. And then finally I need to convert it to what do you call a tensor itself. So I actually defined a function over here, toTensor. So I'm gonna put in that over here. So there's toTensor. All right. And then I need to make sure that all my images are actually of the same shape, because otherwise you cannot put them into batches together, because they need to be of the same shape. That's a very fundamental concept. So for that, I'm just going to do a center crop for now, which means I'm going to be extracting a certain size from the middle. So I'm actually thinking dot center crop. I don't like writing this whole thing, so I'm actually going to define a function itself. So I'm going to be defining that function where I define this toTensor. So def center crop image, return center crop image tensor. Actually, it's a image TSR, right? So I'm going to do center, and finally center crop, right? All right. Similarly, comma, I need to do my y tensors. All right. Y transforms, sorry. And so they're basically going to be the same things, except that I don't need to now convert them into RGB images, because they're by default sort of because they're grayscale images, so any of the the ordering or the kind of transformations don't matter. There's only one kind of grayscale images, like only one kind of one channel images. And so this is going to be basically the entire thing, this over here, except this is not going to exist anymore. That's that. I hope it doesn't give me an indent, an unexpected indent. All right. All right. Right. There is an indentation error. I'm not exactly sure what it is, but let's see. Center crop. Let me put them in one line, so it becomes easier. Alright, and let me put this as well over here. Right, so this would come over here, this would come over here. Unexpected indent. Am I oh, I closed this. What about now? Yeah, okay. So for readability purposes, I'm gonna put it like this. Right. All right. That's my data. So I've sort of extracted my data, and let's take a look at data 0, for example. And that's gonna return me X and Y, right? I'm unpacking the data, and so let's let's actually do one thing. So now data has sort of xf names. So data.xf names is a list of files as such. But now if I type data x comma y is equal to data 0 x dot and so let's take a look at what x is and y is. So x, I expect it to be a tensor. Why not type x, type y. I is not defined. Instead of, I mean, the short should be consistent. I wrote i's over here, but I wrote idx over here, so I'm going to be changing that. And it required one positional argument, size. Okay. So I need to. So I forgot to mention like what exactly is the size that I want to sort of crop my images. And so it's gonna be. So I'm gonna have to initialize it that way. So where is it? Where is it? Where is it? Where is it? Yeah. So instead of, so I'm gonna actually have to initialize it with what size is it that I want, right? 400. So I'm thinking like this is okay. Let me actually put it as size as well over here. No. Let me actually put it constantly. So it's gonna return images of size 400. POSIX path is not callable. Alright. And where did I exactly call anything? Oh, sorry. So I apply TFMS to self.xf names I, right, and self.transforms TFM x TFM list POSIX path. That's weird. Print TFM. Let's take a look. So open and center crop, and then this. YFNI. How about I print X as well? Function. So images data crop dot onb. I do an open at that, and I do a center crop. Once I'm done with that, I do a gt/001. Did I do a print anywhere? All right. X is equal to TFM list. POSIX path is not callable. is it printing it twice? Oh. Y transforms. Oh. Mistake, my mistake. So I sort of pass it through the wrong arguments, but let's see if this works now. Yep, there's still an error. What exactly is data dot y transforms? pl dot open to tensor and center prop. All right, x. Let's take a look at this again. Oops. Okay, so sort of gave it the wrong sort of arguments over there. Yep, it works now. All right, so let me remove the print statements over here. Sorry about that. So the mistake I did was that instead of passing self.y transforms over here, I did self.y f names. So that was a mistake on my part. So you see now both of them are tensors, even though data.x f names and y f names only contains the file paths. All right. And so even though the class itself doesn't take a lot of a memory, but I can still sort of get images on the fly very fast. And so that is exactly like the beauty of like structuring your classes well as such. All right, we're done with that. And if you want to take a look at, let's say, one of them, so x dot shape, you see that it's 400 by 400, which is exactly the shape that we wanted it to be. All right. And so now I need to do my data loader. So train DL is equal to data loader train DS, batch size is equal to 8, shuffle equals true. Right, so I want it to be shuffled because it's always good practice. Valid DL is going to be data loader valid DL. Oh, I didn't do a train test split, did I? So I can't do that. So now right now it's only x and my y. It's only the data sets. So I need to do sort of a sort of a split. So I'm going to defining a function over here that does exactly that. Right. And so I'm going to do def split data set by percent. All right, so it's going to take a data set and it's going to take a percent, which is by default 0.8, so it's going to do an 80-20 split. So by default do a 80-20 split, do an 80-20 split, and right. So I'm simply going to be doing, first of all, percent should be between 0 and 1, right? So I'm going to be asserting that. And if this fails, I'm basically going to return PCT should be a floating point between 0 and 1. All right. Now what I'm going to do, return random split data set, and random split actually takes what do you call integers, like the indices where you want to split. So I'm going to have to do that separately. So int pct star len dataset, and the second argument is going to be len dataset minus this basically thing, int. So let's say that the length of the dataset is like what's I don't even remember. 1630. All right, so it's going to do a 0.8, but it may be a float and you can't sort of index from a point like a fraction, and so you're going to have to convert it to an integer. And so I'm sort of doing this is basically saying that do, let's say, about like what is 16 times 64, 120, so about 1280 images would go into the training images, and the remaining whatever number of data set images there are, pass it to the validation images. Alright, and so when it's gonna basically, so let's see, it's gonna do train ds and val ds is equal to split by ds split by pct, and I'm gonna do data. Alright, so now let's actually take a look at train ds's length and length of the valid ds as well. Invalid syntax. Oh, so it should be a single sign, a single equal to sign. Split by ps, split ds by pct, split ds by pct. Alright, so my training dataset contains 1304 images as such, and my validation dataset contains 326. That's an 80-20 split roughly. That works for me. And so batch size over here, I can sort of double the batch size now, because again I don't need to store gradients for that, and shuffle. You don't need to shuffle a validation dataset either, because anyway there's no training sort of bias that's going to be formed because of validation, because you're not training on the validation dataset. For what do you call the GPU thing, I'm going to define a name is called device, torch.device, CUDA 0 if torch.cuda.is available, right? Else CPU. So let's take a look at device. Valid ds is not defined, so it's val ds. All right, val ds. All right, that's that. All right, so let's take a look at what exactly is it that our data loader will return. So next iter train dl, and so x.shape and y.shape. All right, and so I return 8, 3, 400, 400, 8, 1, 400, 400. All right, that's it. Now let's actually sort of do something very interesting over here, and so what I'm basically going to be doing is I'm going to be implementing, I'm going to be creating my model over here. All right. Right. So I'm sort of creating my model over here. And the model which I'm going to be using is something known as a unit. What exactly is a unit? A unit is sort of a this is known as a unit. All right. Right, give me, yeah, this is called as a unit. I hope you can see it. And so what exactly a unit is sort of, it gets its name because of its shape. It looks like a U on paper. All right. And so the way units actually work is it actually consists of two parts. And so let me actually do a sort of a split over here in between. All right, and let's talk about like why exactly can we not use the kind of architecture that we used before. If you guys remember that the CNN architectures or any sort of neural network architectures that we've seen before, they output sort of a label or a single value, and that can be given by a linear layer, right? So a numerical value or a class or anything like that. But now your output image is actually sort of a map. It's an image in itself, which is of the shape 1, 400, 400, right? And so you can't sort of use a linear layer at the end. You need sort of a operation which returns an image itself, and that is the property of convolutional blocks. And so you need convolution operations itself to sort of return images at the end. And so what people did is that they sort of took two convolution neural networks and sort of put them in reverse. All right, this part over here that goes till the end, this is sort of a linear block over here, and so this is the input convolution block, and so this is the kind of normal neural network architecture, convolution neural network architecture that you would see. And this is sort of the reverse of the same operation. So it takes a linear layer as the input and gives a convolutional map at the output. All right, and so the output is, and the architecture is designed in a way that the sort of images sort of you get the same kind of image at the beginning that you get at the end, so in terms of shape, and then it's the training module's purpose to sort of return images, sort of return the ground truth values in whatever format you want. So over here we want maps, right? And so it's my job to sort of to get an image which is of the format this, and it contains black and white pixels in whatever format I want. All right. Units, and so sort of, by the way, how do you actually go from a linear layer back to a convolution operator? So over here, the linear layer is going to have very less number of features, and over there you have a large number of features. But if you remember, convolutional operations sort of reduce the number of features. So how do you actually increase the number of features back to the original number of size of the image? And so to do that, there is actually known as an inverse convolution or a deconvolutional operation, deconvolution in image processing. And sort of reverse convolution. Deep learning. And so the way it works is that it will take a lower level, low number of features and sort of output more number of features. And so let's actually take a look over here. And the way it is done is actually very simple. Originally we had this blue map of 3 by 3 over here, and what they did is this sort of split it, and they sort of put blank pixels in between of that, so the size increased by n number of size, and then they ran a normal convolution operation on top of that. And so the output image, even though it's you gave it an input of 3 by 3, it would now have a size of a larger of a larger feature map size. Enough of that. Let's talk about the unit architecture. So the unit architecture was introduced back in 2015, guys, in this paper known as Unit Convolutional Networks for Biomedical Images. I'm going to put in the link of the paper over here. And so what we're going to do in this lab sessions, we're going to be implementing this paper from scratch. Right, so it's also a very good exercise for you to know like how exactly is that I go about implementing papers. And so this is the architecture that we're going to be utilizing over here. So you see that it takes a certain image of a certain size, it does certain operations, and you see they're over here. You get a linear layer size of 1024 features, and then you basically sort of go back up and you get the map of the same size of a particular size over here. All right. Now over here, this input size and the output size don't match, but it's our job to ensure, we're actually going to be modifying that to ensure that we get of the same size.
What's the gray line showing? Because it's doubling, like there's a white extra portion.
All right. Good question. That was actually going to be my next line. And so you would actually notice some extra things over here, which are these gray lines which says copy and crop. What exactly they are. Here's the thing. You are trying, like, let's throw away the left part of this model. So there are only 1024 features over here. All right, and you're expecting 388 times 388 features, which is like what, 300 and 388. So that's 150,000 like features out of just 1,000 features. And so it was actually hypothesized that these 1024 features are not going to contain enough information to represent all this information over here. So what they did is that they, like, instead of just sort of having the features that you extracted out of the up convolution or the deconvolution operation from 1024, they also copy pasted this processed convolution map over here, and we're going to ensure that they two are going to be of the same size, and those two are going to be concatenated, and further convolution operations are going to take on top of that. And so this is a sort of a way to retain information. This is, in machine learning lingo, this layer is called the bottleneck layer because it's the smallest in size. And so this skip connection method is actually one of the most famous methods to retain information through these bottleneck layers. That's about that. Read this paper.
So like the layers on the left side, they are giving their outputs to two different layers up ahead.
Yes.
Okay.
Yes. So let's actually build a convolution neural network, and we're actually going to be building something on the lines of this, all right, but using the same sort of concepts. So I'm going to be defining. All right, so if you guys see over here, you have convolution followed by a ReLU. Nowadays, we also use something known as a batch norm, which in the sense we sort of normalize each layer after a convolution block batch wise. And this is a way to sort of reduce bias, because otherwise you'll see that your activations sort of you start facing what do you call, gradient exploding or gradient vanishing. And the reason for that is because there's a sort of a shift in the mean average values of all the pixels, right? So for example, let's say the average value for now is let's say 10, all right? And so let's say let's say the convolution operation sort of shifts the sort of the mean value by 1.1 in average, and you're gonna be running 1.1 again on top of that for a different batch, and so on and so forth, and you're going to be running it for many iterations as such, or you're going to be running it for many layers as such over here. Like there's 1, 2, 3, 4, 5, 6, 7, and 9, 10, so on and so forth. So let me just raise it to the power of 10. So by default, the input size is going to be very large, and that's going to affect the gradient size as well. There's going to be exploding gradients, and your model is going to crash. So after each layer, you sort of normalize it and bring the average back to 0 for that particular batch. So that's called batch norm as well. And you'll see that this convolution block, this operation conv 3x3 operation, which is the conv 2D operation that we see on the last, ReLU and batch norm sort of always occur together. So I'm going to name them as class block, right? Sort of to make my life easier. I'm going to name it nn.module. And I'm going to initialize this as so there's self, in channels, and out channels, because that's what my convolution operations cares about. Always initialize what do you call, the super.init for nn.module, self.conv one. Okay, let's actually talk about what exactly I'm talking about. And over here, after the batch norm as well, there's something else that you want to take care of, which is that you'll always see that these two convolutional blocks always occur together, right? And so to make my life easier, I'm actually just gonna write them together. For now, I'm gonna skip batch norm because it's not part of this paper, but I'll show you how we'll add it later on and it'll actually improve the accuracy. So I'm gonna name it self.conv1 is equal to nn.conv 2d in channels and out channels, right? Right. And so, right. So look at this over here, that this takes in one channel as input and 64 channels as the output, right? Now over here we have RGB images, so this in fact has 3 channels rather than 64 channels over here, and but the second convolution prop is basically 64 to 64 itself. So that's that, and self.relu is equal to nn.relu, all right, and self.conv2 is equal to nn.conv2d out channels and out channels, right? And because of the reason, I'm basically implementing the paper at this point, all right? But in a very modern object-oriented programming manner, and in a very sophisticated manner as such. These are all 3x3 convolutions, right? Right. And so by default, let's actually take a look what exactly. You see, by default kernel size, I need to input 3 as well. So kernel size is 3. Alright, there is no padding and there is no stride as such. Stride is just 1, padding is 0. This is given in the paper because you see 572 is converted to 570, so there has to be 0 stride and 0 whatever. That's my initialization as such, and then I'm gonna do a def forward, right? It's gonna be self x, and that is gonna be simply return self.relu self.conv2 self.relu self.conv1x. If this is confusing, by the way, maybe I can just do layers is equal to self.conv1 self.relu self.conv2 self.relu again. All right, and now what I'm going to do is that for layer in layers, x is equal to layer x return x. All right, that's a better way to sort of represent it. And now let me actually show you if this is working. So let me for example put it. So by the way, this part of the operation, which is this part that goes down, is actually called the encoder, because encoding basically means you're sort of putting in raw images and getting processed features, so that's called the encoder. And the opposite part is called a decoder, because you're putting in basically the opposite, you're putting in features and you're getting raw images outside. So let me just name this encoder block. In channels is like 1, so 1, and out channels is 64, 164, 164. Let me actually initialize a random sort of tensor, 1 batch size, 1 channel, and what was the size? 572 by 572, right? So 572, 572. All right, and let's actually pass it through that and let include block x dot shape. All right, so is equal to block relu. Right. And so now you say it's 1 times 64 times 568 by 568. That is exactly 64, 568 by 568. So this block is now working. Now that's about that. All right. So now I'm actually going to be defining my encoder in general, which is this part, this entire part over here. All right. And so you look at this, this contains 1, 2, 3, 4, and 5 different sort of blocks in general. All right. And so let's actually take a look at that. So I'm going to be defining class encoder. It's going to be nn.module again. So I'm basically dividing my model into two parts, encoder and decoder. All of them are classes. All of them have to be classes. All right. But what I wanted to appreciate more than like me defining this is like how organized this is in terms of in terms of classes and stuff like that. So otherwise, like all other implementations that you're going to be see on the internet is basically them listing them out sequentially. So conv1 relu, conv2 relu. It's very haphazard. It's very hard to read as well. What I'm doing is basically sort of organizing it in a better way. So now my input has to be 3. By the way, default list. My input number of channels is going to be 3. Next is going to be 64, right? Next is going to be 128, 256, and 512. So 128, 256, 512. All right, and finally 1024 as well. All right. So there's 1024 channels, and the image size is going to be whatever. I mean, this image size is going to vary because our input sizes of different sizes. So I'm inputting 400 by 400. But the thing with you must have seen that whenever we in fact defined our convolution neural network model in the end, whenever we did average pooling, we used adaptive average pooling, and the reason we did that is because we wanted to make the model independent of the size of the input. So even if you feed it like 400, 400 images, or you feed it 800, 800 images, your neural network model is going to learn regardless. And so we actually don't care about the size of the images, but we do care about the channels, because channel is something that you have to control as such. So super.init as always, right? And self.encoder blocks is equal to, I'm going to define a list over here. So, but it's going to be nn.module list, because then I don't have to sort of register each of them separately as such, and the reason I'm doing that is because these themselves, I didn't register them as blocks anywhere, because these were not my final models. But now I have to sort of define them as models. So nn.module list is a very convenient way to do that. So I can put in a list of models, and it's gonna iterate through that list, define it as modules, and it's gonna store it as sort of modules of this particular list over here, of this particular model over here. So this is actually going to be fairly, so I'm going to do chsi and wait, okay, it's going to be chsi plus 1. All right, for I in range len chs minus 1. So what I'm basically doing is that I'm iterating the list, and I'm saying that first there's a block which in input channels is 3, output is 64. Next goes 64, 128, 128, 256, 256, 512, and finally 512, 1024. That's that.
Yeah, will you make the encoder and decoder separately?
Yeah. Yes.
So you will need one other function to take the outputs of the different layers of the encoder to combine it with the decoder.
Yeah, we'll do that. But and that's pretty simple actually, because I've now basically, that's the reason I've sort of saved them together as encoder blocks, right?
Hmm.
And so what I can do is whenever I'm going to do that, I'm just going to go and sort of do a sort of a connection, and we look at that. It's actually quite elegant.
Hmm.
You like it.
Okay.
Self dot pool. So there's a pooling layer over here, and you can choose what kind of pooling layer you want. Oops. And that's max pooling, right? Max pooling. So I mean, nowadays people use different sorts of poolings, but since we're implementing this, why not? So nn dot max pool 2d 2d. And so by the way, this is a 2x2 max pooling, which means that what max pooling basically is that it sort of goes in sets of 4s, and it will filter out the maximum value out of that. So you're sort of reducing each image by a factor of 4. Take a look at it, but there's going to be 2 over here. All right, that's that. All right, so that is done. Now def forward is simply self comma x, and I'm actually going to be defining a list called features, and the reason I'm doing that is because I don't because forget about I don't really care about these outputs. I care about these outputs because they have to go into sort of what do you call they have to go into the decoder block as well. So I can't simply return the output of this final model. I have to return the outputs of all these sort of outputs over here. So I'm going to be returning that in a list called features, and here is the answer to who was that who asked this question about me having to take care of the skip connection things. Okay.
I guess it was Shaurya.
Okay. Yeah. So Shaurya. So so unlike previous models, I'm not actually returning the output of my final layer. I'm actually simply returning the list of all the features of all these encoder blocks. So
Okay.
for block in self dot encoder blocks, right? X is equal to block X. All right. Features dot append X. All right. X is equal to, now by the way, pooling. So this part before pooling is actually the feature which I need to send to the encoder block. But once I'm done with that, in order to send it back to the next layer, I'm actually going to have to pass it through the max pooling layer over here. All right. So X is equal to self dot pool X. All right. That's that. And finally, once I'm done through this, I'm going to return this features list over here. All right. And that basically is my encoder part of this. Invalid syntax. Oh.
Also, is there like a module which does all this on its own, or if we have to implement a unit model kind of thing on our own for some purpose, then we have to do all this manually?
Sorry, I didn't understand.
Like these block, you created a block and then you made a encoder class and then you're using those blocks in it.
Right.
Is there a module which makes this easier, or is this the easiest that it gets? Like, because this is
Module
getting
of
a
what? I
bit
didn't understand.
like this is getting a bit complicated. Like lots of things to write and all. So like you had like sequential, something like a sequential in the other one. In
So
this
okay,
the
let's actually talk about like what exactly sequential would look like. So you would write a sequential block, and you would pass in conv 1,64 relu batch norm 1,64 relu batch norm 1,64 batch norm max pool 64, 128 64, relu 64 128, and you will keep on writing stuff like that. What I've done over here is I've sort of reduced this operation into one class all these operations into one class. And so all I need to define is what is the input, I need to define these intermediate 164, 128, 256, 512, 1024. That is everything that I did over here. And now it will basically define all those functions from here to here, which is a huge list, by the way. So I wrote about, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So 15, and then I would have to sort of store these as well. So 16, 17, 18, 19, and then 20, which is the output of this. So 20 functions in this small line, which is basically in one single line, in two single lines, self.encoder blocks and self.pool. So how much easier do you want it to be?
No, I mean, no, it's easy, okay, but
This is okay. I get what you're trying to say. I guess what you're saying is that
we've used our brain to do it, is what I'm saying.
but here is something that I also want to point out. Now, suppose you were to write a sequential block, and then for sequential blocks, you would have to sort of take care of the inputs and output size as well. What happens when you want to use a different architecture? You would have to sort write all of that from scratch again. Right now, all I need to do is I need to change either my block, or I need to change my number of channels. Right. I mean, so I personally find this more flexible for the user, but as software engineers or as coders, I think it's very important to understand how do you structure your code well. I think this is a very important concept that I like all of you to learn. Anyways, right, encoder works. Let's see if my encoder works. So encoder is equal to encoder, right? X is equal to torch dot random 1, 3, 572, 572. All right. Features is equal to encoder X, and for feature, in features, print feature dot shape. All right. All right. So now let's take a look at. So there's 1, 64, 568 by 568. All right, that makes sense. Then next should be 280, 280. So that's 280, 280. 128, 28. And then there's 256, 136, 136. So 256, 136, 136. All right, 512, 64, 64. So 512, 64, 64, and 1024, 28, 28. So 1024, 28, 28. So now we have implemented the encoder, and it's literally the implementation of this paper. All right. So now I need to do sort of a deconvolution. So the deconvolution part. So I apologize, but I'll like to take this lab a few more minutes, and then if we cannot reach a feasible point, we'll sort of continue next lab on this. It's a very interesting thing. I'm thinking of sort of continuing this lab session. Okay, no, but I'll sort of take it next week. That's okay. So there's class decoder nn dot module. All right. Def init self channels is equal to, let's talk about what they are. 1024. Let's talk about 1024, 512, 256, 128, 64, and then 2. But I want the number of output channels to be 1 because I have only one channel to be predicted. So 512, 256, 128, 64, right? And then I'm gonna leave the output channel as is, because this is sort of I will take a look at this later on, but I want to sort of give it some sort of leeway as to some sort of flexibility, but we'll take a look at that. So, and this part, up until this part over here, this very last layer is actually called the head of the it's called the body of the neural network, right? Which is basically everything that remains constant, even if you want to transfer learn it, and if you want to simply change it to another problem, all you need to do is change the first layer and change the last layer, and the remaining remains the same, which is why I'm actually keeping my decoder till here. And so, simple, I'm gonna do super dot init, right? And now what I'm gonna do is that self dot channels is equal to channels. That's what I did. I didn't do that over here, but it's sort of tricky. Now here comes the slightly tricky part, in which what I'm gonna do is that self dot upconfs is equal to nn dot module list nn dot conv transpose 2D, which is basically the deconvolution operation that I talked about, right? 2D. It's gonna take in channels I. Let me this channels I plus 1, right? For I in, and by the way, what else do I need? So nn dot con transpose 2D, sorry. Okay, so let's actually take a look at nn dot conv transpose 2D. Alright, and I want to look at the initialization signature. So it takes in kernel size, stride, and stuff like that. So by the way, up convolution is a 2x2 operation over here. Alright, and there is a stride as well, which basically means like how much spaces you want to insert between each pixel of the input images. So that's going to be 2, and the pixel is going to be 2 as well. I'm not exactly sure kernel size and stride. So so the stride has to be 2. Let me see if they've mentioned it anywhere. Right. At each downsampling step, we double the number of feature channels. Right. Every step is expansive path consists of an upsampling of the feature map, followed by 2x2 convolution that halves the number of features, a concatenation with a corresponding crop, and 2 3x3 convolutions, each followed by a ReLU. This crop is necessary due to the loss of border pixels. At the final layer, a 1x1 convolution is used to map each 64 component into data. So this is the final data we're talking about, so we'll do that separately. And there is a stride of 2 that you have to include in that. So that's what I'm basically doing over here. So for I in range len chs minus 1. Alright, that's that. That's the up convolution part. Right, and then followed by that is basically, once you do the up convolution part, you can basically do the same block, 2 convolutions followed by that. So that's basically nothing but self dot decoder blocks probably, and this is going to be nn.module list, simply nothing but block chs I plus 1 for I in range len chs minus 1, right? That's it. What will def forward look like? So that's self x. And now here comes the interesting part. So what I'm going to do is that for I in range len chs minus 1, I'm going to go x is equal to self dot upcons I x. So what I'm basically doing is that whatever output I'm getting from here, 28 by 20, and I'm first upsampling this, so I would get this blue box over here. To that I need to concatenate whatever features I got from my encoder blocks over there, right? So here's something interesting. Instead of just x, I would also need to pass it my encoder features, right? And so what I'm going to do is that encoder features is equal to self dot crop okay, so here's what I need to do. I need to sort of do I need to make sure that if you see over here, there's a sort of a cropping operation going on over here, because this shape is not necessarily equal to the shape that you get over here. So you need to make sure that you crop certain number of features that are equal to this size. So that's the only way you can concatenate them. All right. So for that, I'm going to be, so you look at that, there's copy and crop. So I need to do that cropping operation as well. So I'm going to define this self def crop self what features and then x itself. So what I'm going to do is that I need to first define what exactly is the height and width of my x, right? Because that's going to be the shape which I'm going to be using to crop my features. So I'm going to do torch vision dot transforms dot center crop, right? And I'm going to be defining what size is it that I want it to be, and I'm going to be passing it the feature to it. All right, and I'm going to simply return feature. So what I'm going to do over here, that feature is equal to self dot crop encoder features I, which is basically the feature corresponding to each list. But here's a problem. I need to also reverse it. I need to reverse the features in order to sort of concatenate them in order, because my model is going to be returning this, and this in this particular order, but I'm going to be getting this as the very first input, very first output in my decoder layer. So I'm actually going to have to reverse the feature list in order to match them as such. So what I can do probably is that encoder features is equal to encoder features that is minus 1. Also my encoder feature also contains, let's say, this as the output. So there is no concatenation going on over here, so I need to sort of remove that as well. So I'm going to be starting it from the very first index rather than anything else. I get it, it's like sort of confusing, but that's the nature of the paper as such. It's not as difficult as you seem. Once you sort of develop this, you don't need to run your brain at any point. You can simply just use whatever this entire format in whatever way you want. And so right, that is that. Now you need to do sort of a concatenation. So you do torch.cat, which is concatenation. You do x feature All right. On the first dimension is equal to 1 because dimension 0 is the batch. You don't want to concatenate the batch. And x is equal to self dot decode blocks I x. All right, that's that. Let's see this works. So decoder is equal to decoder. All right. X is equal to torch dot random 1,1024. What's the input size? That 28,28. All right. And decoder is equal to x. So decoder x encoder features will be FTRS. All right. And dot shape. CHS is not defined. Where? Len self dot CHS. Missing one required argument x self dot crop. Right. Okay. Self dot crop this and x itself. None type object has no object shape. I didn't return anything, so that's my mistake. So I'm going to be doing a return x over here. Alright, so let's take a look at this. The output size is 388 by 388. This one, 64 times 3. I haven't defined this final layer as of yet, but it's 388, 64 by 388 by 388. That's 64 by 388 by 388. Alright. And so I'm going to take 5 more minutes and I'm actually going to be putting them together in one big model. Alright, and I'm going to be naming this as my unit model. Alright. For this, I'm actually going to be using there is something that I need to do is that I can probably stop whatever I'm doing over here, and all I need to do right now is sort of I can probably take this as as the input and sort of okay, and here's the problem that we're going to be facing. So 572 is the input, but 388 is the output. So what I'm going to do is I'm probably going to be interpolating 388, 388 to 572, 572. All right, and that's going to make sure that the input and the output are going to be the same size. So for that, I'm going to be needing the torch.nn.functional. So let me actually put a text over here that says that putting them all together in one class. Right, torch.nn.functional as f. All right, and I'm going to be defining class unit. All right, which is going to be nn.module def init. So let's see what exactly is it that this needs. So it needs encoder channels, right? Encoder channels, which is going to be this by default. Or let me not actually put that, but okay. Encoder channels, it needs decoder channels. CHS is a better word actually. Alright. Num classes, which is number of classes that you want, is going to be 1 because, well, number of classes is 1, which basically means that because it's a binary classification problem, so there needs to be only one output channel. Retain dim is equal to false, which means that do you want to sort of retain the dimensions of so you have the option to either sort of interpolate it to 572 by 572 or take it as it is, however you want it. It's going to work either way. But that's our option that you have. By default it's false, which means it will be interpolated, and out size is equal to 400 by 400. And so first, of course, super.init, right? And so after that I'm going to do self.encoder is equal to encoder encoder CHS, self.decoder is equal to decoder decode channels. I'm going to have self.head, which is going to be the final, and so I talked about the body of the neural network model. Now I'm going to be talking about the head, which is basically this part, which is basically the part which you can sort of optimize, which you can sort of change according to your problem. It's called that, and it's nothing but nn.conv2d, and so it's going to have decode. It's going to have whatever number of channels are at the output, which is 64, which is decode CHS -1, comma num classes. So if there are, so for example 10 classes, you would need 10 different channels as such, but now right now I need only one because it's a binary classification problem, right? Oh, sorry, this is num class is basically I mean the number of channels essentially. It's sort of a misnomer, but num out ch. So let me do num out ch. Alright, and this is basically a 1-by-1 convolution operation. Right, green is a 1-by-1 convolution operations. So it's nothing but it's a 1-by-1 convolution is nothing but a linear layer, right? But it sort of goes iteratively through the image and it gives an map back without sort of breaking apart the image. So that's why 1-by-1 convolution. Finally, self dot retain dim is equal to retain dim, and self dot outsize is equal to outsize. I'm going to do a def forward, which is going to take self x, and what's going to do encoder features is equal to self dot encoder x, out is equal to self dot decoder, and decoder sort of takes in x and the features, encoder features themselves, right? Right. Right. Not x, sorry. The output of encoder features, which is, I mean, the output of this is basically the very last element. So we actually stored this element in encoder features as well. So it's going to be encoder features -1. All right. And encoder features themselves, the entire whole, and out is equal to self dot head out, right? Finally, if self dot retain dim, right, out is equal to f dot interpolate out self dot outsize, and finally return out. Yep. So let's actually initialize this model. it's simply going to be unit is equal to unit retain dim is equal to true, right? Dot CUDA, not CUDA as of now. Oh, okay, dot CUDA, because I need to sort of run it very fast, otherwise it's going to be very slow. XY is going to be next iter train DL, right? X is equal to x dot CUDA unit x dot shape. Oh, I didn't input the encoder and decoder channels. So my encoder channels is going to be this, right? And so what I'm going to do over here is that encoder CHS is equal to this, decoder CHS is going to be this. And so over here I'm gonna have this, right? The encoder channels is equal to encoder CHS, decoder channels is equal to decoder CHS. Hopefully it works. Torch.size is not callable, and where did I do that? Oh, see. So my input, we also print x.shape. And so so my input was 3,400, 400, output is 1,400, 400, and that is basically the implementation of the unit architecture. So next time we're actually going to take some time to okay, and let's say what exactly does unit look like. So look at this unit block, and so look at what module. So you can now print it very easily, and it's a very beautiful illustration of what unit exactly is. How we didn't actually define dunder repro for units, but because we passed it through what do you call module list automatically does that for us. All right. So encoder blocks, so it also divides it into whatever. So unit consists of two parts, which is encoder and decoder. Encoder consists of encoder blocks, right, which is module list block 1, block 0, block 1, block 2, block 3, block 4, followed by a pooling layer. Decoder consists of these things, and so look at and there's the head as well. So that's how beautifully it sort of puts them all together. Right, so I'm gonna stop this lab session over here for now, and next lab session, ideally I would like you guys to sort of build the remaining part on your own. It's as simple. You already have the learner class function which actually wrapped all of this together and did the training cycle. All right, you can do that on your own, but we're going to take 10 minutes from next lab session and going to do this. And then next lab session we're also going to be starting with RNNs, and so it'll be quite interesting. All right, so see you guys next lab. Sorry guys for whatever delays that we had today. I'll make sure that it's incorporated, and this lab session recording will be put on the website. Alright, so see you guys next lab session. Hope you guys learned something new today.